All right, so copies of. You'll see this is going to be very useful to us. And another thing that's going to be useful to us is this. As you look at this screen right now and we think about 5 times 3, 5 copies of 3, do you notice that right now there's nothing on the screen? We start with nothing and then we do what the operation says. We start with nothing and then we create 5 copies of 3 because that's what the problem says. 5 times 3. If you use my copies of language, it says we need to create 5 copies of 3. Or in other words, the way I'm going to say it here, come on. We need to place on the table, let's pretend we were working on a tabletop. We need to place on the table an amount that is equivalent to 5 copies of 3. Now I'm going to ask you, just pause the video for a minute, get on those virtual manipulatives, and just go through the act. Because what's going to happen inside of your brain as you go through this is going to be very valuable for when we get to, say, a negative times a negative. So, your task, pause the video, go to your virtual manipulatives, and place on the screen, in this case, an amount that is equivalent to 5 copies of 3. And after you do that, come back and see what I do. Did you do it? I hope you did. 5 copies of 3. I hope it looked like this. Now, in my PowerPoint, my positive chips are white with the little plus sign. In the virtual manipulatives, you probably use the yellow for positive and you'll use red for negative. But so far, just the positive chips are all that's needed here because we need to create 5 copies of 3. So we would create a copy of 3. We would create a copy of 3. We would create a copy of 3. There's 3 copies, 4 copies, and 5 copies. So 3, 6, 9, 12, 15. We have 15 chips on the table now. So when you created 5 copies of 3, it looks like this in some way that you organized it. Maybe you didn't organize it as like Mickey Mouse ears here. Maybe you organize it differently, but 5 copies of 3. All right, now. Oh yeah, and there's the 15. Now what about this? This says 5 times negative 3. Now again, go back to the thinking about what multiplication means. 5 copies of negative 3. Now you've been reading a lot about rushing to algorithms, so you have to imagine that if I'm working with 6th graders, and I'm saying 6th graders, I've done this unit with 6th graders, and we don't rush to the algorithm. There are no algorithms, there's no rules, there's no ways to remember how to do this. We're just asking students to think about what 5 times negative 3 means. We're going back to the meaning of multiplication and allowing students to play. They've got manipulatives on the table, or most recently I had yellow and red counters magnets, and they're up at the whiteboards. And they're working at the whiteboards, putting those magnets up to make 5 copies of negative 3. So again, here's your thinking. Create, because it's a positive 5, so we're creating 5. Multiply means copies of, 5 copies of negative 3. Will you please pause the video, go back to your virtual manipulatives, and let your brain think through what would it look like? What would it feel like? What would your brain be doing if you were thinking, oh, look, I got 5 copies of negative 3. Pause the video and give it a go. Did you pause the video? Let's go 5 copies of negative 3. So now we're creating on the table an amount that is equivalent to 5 copies of negative 3. So you'd make 1 copy of negative 3. You'd make 2 copies of negative 3. You'd make 3 copies of negative 3. You'd make 4 copies of negative 3. You'd make 5 copies of negative 3. You have 5 times negative 3. What do you have? Clearly, 5 copies of negative 3 means you've got 15. Now, can I pause here for a minute? Will you please think with me? When we rush to the algorithm, do you remember Gretchen? When we rush to the algorithm, sometimes students do this. They go, oh, I remember. If the signs are different, like a positive and a negative, I remember the teacher said once that when the signs are different, you take the sign of the larger number. And so they would look at this situation because they never made sense. Let's just pretend for a minute. They never really made sense of things. They just are remembering rules that made no sense. And what happens then, we get Gretchen situations where students apply the rule, a correct rule, but they apply it in the wrong case. With addition, you would take the sign of the larger number, in this case the positive, but not with multiplication. So when we don't rush to algorithms and we allow students just to think about what multiplication means, you're not going to get that issue of, oh, I'm trying to remember, let's take the sign of, is this one going to be positive because 5 is bigger than 3, so I'll take the positive sign. No, they just think about multiplication. 5 copies of -3, and you can imagine it. Eventually, we're going to not use chips. Kids can't just carry counter chips in their pocket everywhere they go, every time they have to multiply. Instead, it might become a visual in their head, and they think, oh, 5 copies of, I see a -3, a -3. If I had 5 copies of -3, I would just have a whole bunch of negative chips. 5 times 3 is 15, so I'd have 15 negative chips, 15 red chips, and so I know my answer is -15. And it all flows from the thinking, not from remembering a rule that may or may not make sense. I hope you're following my train of thinking there. All right, so now, positive 5 times -3 says I need to create 5 copies of -3. We need to place on the table an amount that's equivalent to 5 copies of -3. But what happens when you have something like this? Now, what I want you to do is pause the video and just take a moment to think. How would we interpret? How would we think about? What would the meaning be for -5 times 3? Will you pause and think about that for a minute and then come back and hear what I have to say? What are you thinking? How do you create -5 copies of 3? It's kind of a weird thing, isn't it? So we have to do one thing here. And this is going to mathematically add to our understanding of what a negative number is. I'm showing you a number line here because negative numbers have another interpretation that's going to be really valuable to us here. Look at this number line. 5 is to the right of 0. -5 is to the left of 0. We often say that 5 and -5, for example, are opposites. The opposite of 5 is -5. Opposite in the sense of positive is to the right, negative is to the left. And that's a way that mathematically and in science, a negative sign often indicates a direction, not literally a quantity. Like, how do you think about -5 as an amount? Remember the conceptual challenges historically that we had is it's really hard to come up with a physical representation of a negative quantity. So rather than thinking of it as a negative, as some weird thing, think of it as opposite. The opposite of. Opposite in this sense. +5 is to the right of 0 on the number line. -5 is to the left of 0 on the number line. And so I'm going to encourage you to interpret a -5 as the opposite of 5. And let me just convince you, I hope you're convinced, that this is mathematically true and powerful and useful to add to our understanding of negative as the opposite of. So, the opposite of 5 copies of 3. Will you pause the video now? Go to your virtual manipulatives and just ponder that for a minute. How do you think kids might conceive of, if they're thinking about 5, a -5 is opposite of, if they're interpreting this little statement here, opposite of 5 copies of 3, what might they do? Go ahead and try for a minute and then let me know. Come back and listen to me tell you what I know about how this works. All right, -5 times 3, the opposite of 5 copies of 3. So let me back up here for a minute. So, oops, I went too far. So 5 times 3 meant we need to create 5 copies of 3. So what would -5 times 3 mean? And this is how, I told you I've done this with 6th graders, when they were thinking about it as the opposite of, and by the way, that means there's a teacher in the room who is asking questions and pushing students to think, having conversations. This doesn't just happen without teaching. But when students are in a situation like this and they're looking at 5 copies of 3, and then you say, well, what do you think -5, the opposite of 5 copies of 3 would look like? There's some students that would go, well, the opposite of that would just be to flip the counter chips over, make the yellow chips red. And so the opposite of 5 times 3 would be -15. Since 5 times 3 was 15, the opposite of 5 times 3 would be -15. And certainly that's a wonderful way of thinking. And another way of thinking would be this. Look on this. With 5 times 3, I said we needed to create on the table an amount that's equivalent to 5 copies of 3. What if we interpreted this to say we need to do the opposite of creating 5 copies of 3? We need to remove 5 copies of 3. So 2 ways to think about this. And let me tell you, this is not the teacher saying, hey kids, let me show you all the ways. In my brain, there's no showing. In my brain, it's kids thinking, working together, collaborating. They've got tools, they've got manipulatives, they have meanings, they know what multiplication means, they know that a negative is an opposite, and they're thinking, and I'm letting them productively struggle. And as they're productively struggling, some student in the room says, hey, well, 5 times 3 was creating 5 copies of 3. The opposite of that would just be to flip them over and make the yellow chips red. Should be -15. And then we talk about that. And I'm like, Johnny, that was fantastic. Can you convince us of your thinking? And the class maybe gets convinced of the thinking, and we right there make that Johnny's rule. But then another student in the room might think, well, when we were creating 5 copies of 3, wouldn't -5 times 3 be the opposite? And we need to remove 5 copies of 3. And let me just remind you that back here, I made the point that 5 times -3, we start with an empty table. There's 0. And then we created 5 copies of -3. Well, likewise, in this case, we need to start with 0. And then from that 0, remove 5 copies of 3. The negative meaning to remove. So look, what do I have? I hope this brings you back. We have a sea of zeros. So even with 5 times 3, we started with an empty table and created 5 copies of 3. Now we start with not a literal empty table, but a representation of an empty table, because every time you make a positive and a negative together, you have 0. How far did I go? There we go. Okay. Now, I start with 0, and because of the negative, interpreting negative as the opposite, instead of creating 5 copies of 3, I need to remove 5 copies of 3. And notice that the 3 is positive, so I'm going to remove 5 copies of 3 positive chips. So I remove 1 copy. I remove 2 copies. I remove 3 copies. I remove 4 copies. I remove 5 copies. Any additional 0 pairs don't matter, and look what we have here. We should have 3, 6, 9, 12, 15. We have 15 negatives. Look at that! There's a couple of ways this might show up as a problem to solve. Listen to this. This is a problem for students to solve. You start off with 5 times 3, they create it. Put 5 copies of 3 on the table. They do 5 times -3, they create it. They create 5 copies of -3. And then you give them one day. Now this happens over days, you know. This is after lots of practice and thinking. But then one day they come in and you go, what about -5 times 3? And they go, whoa, that's weird. What would be a -5 copy? How do you make negative copies? Then you have some conversation and you ask questions, and we get to the point, like the number line, you go, well, -5 is just the opposite of 5. So it's the opposite of 5 copies of 3. What do you think of that? Go, get to work. And a student makes 5 copies of 3, yellow, and then says opposite would be red, -15. You talk about it. Another student says, well, before we were creating, starting with 0, we created 5 copies of 3, we made 15. Well, now we have to do the opposite. We have to remove 5 copies of 3. And we've already learned about the sea of zeros. So they make a sea of zeros, and they remove 5 copies of 3, and you're left with -15. Now, there's lots of cool things either way. Either way, it's so cool because now students have a tangible thing to think about. If 5 times 3 is, I'm thinking I can see it in my brain, 5 copies of 3. I can see all these yellow chips. Well, the opposite of yellow chips would be red chips. Or I can imagine, instead of creating 5 groups of 3, if I had to remove from a sea of zeros, if I had to remove copies of positive 3, well, if I'm removing the positive, what's left is the negative. And so a negative times a positive is a negative. Woohoo! We let the students develop that. We talk about it, and we make it a rule based on the class. You know, the class's rule, Johnny's rule, Sally's rule, whoever it is. We make it a rule based on the student thinking. All right. You know what's next? We got to get to the negative times a negative. But before we do, I want you to just stop and think. What do you think's going to happen with a negative times a negative? Will you pause the video, think about it, and give it a shot? Before I go into this, I want to share something. I started teaching in 1988, and I think it was 1987, a movie came out called Stand and Deliver. And in this movie, it's about a teacher named Jaime Escalante. You should look it up. It's probably streaming somewhere these days. I had to watch it back on VHS. But Stand and Deliver is a movie about Jaime Escalante, who went into inner city LA, and he taught in a difficult school, difficult circumstances, but he taught them to think about math. And it's a great movie. And in that movie, I remember I was a young teacher, and I saw this part of the movie. Check it out.
Means multiply. Every time you see this, you multiply. A negative times a negative equals a positive. A negative times a negative equals a positive. Say it. A negative times a negative equals a positive.
Say it. A negative times a negative equals a positive. Again. A negative times a negative equals a positive.
A negative times a negative equals a positive.
Louder.
I can't hear you. A negative times a negative equals a positive. Louder. A negative times a negative equals a positive. Louder.
A negative times a negative equals a positive. Why? So I saw this clip, and I walked into my class the next day, and I did the same thing. I'm like, a negative times a negative equals a positive. I can't hear you. And the class is screaming, a negative times a negative equals a positive. And then I said, why? I didn't know. I didn't know why. I didn't know how to answer that question. And now I do. How do we think about a negative times a negative equals a positive? Well, there's a couple of ways. One way would be to interpret that negative sign as the opposite of 5 copies of negative 3. Can you imagine it? 5 copies of negative 3. 3 red chips, 3 red chips, 3 red chips, 3 red chips, 15 red chips. 5 copies of negative 3. Well, then that leading negative sign is the opposite. So all those red chips become yellow, the opposite. And so negative 5 times negative 3 is positive 15. Beautiful. So at this point, some students are going to figure that out. Because remember, we'd already done negative 5 times 3. Fully discussed it, worked it through. We got them there. So now this one's probably somebody's going to go that way. 5 times negative 3. 5 copies of 3 red chips. The opposite of that would be positive 15. But other students are going to say, well, what about the creating and removing? You know, with the positive 5, we created 5 copies of whatever. With the negative 5, we're going to do the opposite and remove an equivalent that's equivalent to 5 copies of negative 3. And so you got to start with your series of zeros. You start with an empty table. Now, I don't mean literally empty. I mean empty in the sense of 0. That's a representation of 0. Whoops. And then from that representation of 0, instead of creating 5 copies of negative 3, we're going to remove 5 copies of negative 3. And if you remove the negatives, if you remove the red ones, 1, 2, 3, 4, 5, and then get rid of the extra zeros. If you remove the red ones, what's left? The yellow ones, the positive ones. And so yes, a negative times a negative equals a positive. Why? Because we took away all the negatives, leaving you with positives. Or we did the opposite. We flipped them over from red to yellow. Whatever works for you. A negative times a negative equals a positive. Isn't that great?